So very good morning for all those who are from the UK, and a good afternoon to the Indian participants. We're waiting for Dr. Wallis to log on. Yeah, so he is in the process of logging on, and as soon as he joins us, we will start the formal proceedings. So we'll start formally now. A very warm welcome to all the participants from UK. Dr. Wallis, we welcome you. We were waiting up, all the participants were waiting up for you to log on, and thank you so much for your patience. A very warm welcome to the launch of our webinar series on sports nutrition. As you all know, September has been declared as the National Nutrition Month in India. A month-long focus on nutrition encourages every nutrition professional not only to implement, but to create awareness regarding evidence-based practices related to their area in food and nutrition. Encouraging best practices in the field of sports nutrition, the MIAS, National Institute of Nutrition, Department of Sports Science of the National Institute of Nutrition takes this opportunity to launch its series of webinars on sports nutrition. These webinars have been planned to build capacity of the concerned professionals and generate awareness amongst athletes and the general population with respect to nutrition for sports performance. Each webinar is structured in a manner to give one research-based evidence on a key area in sports nutrition, followed by a session that encourages skill enhancement or sharing of best practices to sharpen skills and practices of sports nutritionists. As the topic of the series suggests, beyond the realm of books or textbooks, we attempt to take you beyond the realm of books into the current real-time research evidence and skill enhancement. So once again, on behalf of our director, Dr. Hemlata, the head of the academics, Dr. Bharti Kulkarni, head of the sports, the administrative head of sports sciences, Dr. M. Maheshwar, who's also the member secretary, and that on my own behalf, I extend a very warm welcome to each one of you. Thank you for your patience and thank you for joining us today. On that note, I call upon Dr. Bharti to kindly give the introductory address. Dr. Bharti, please. So Dr. Bharti is occupied with a certain task and will be joining us soon, or she will be sending her introductory message to us to read up. May I request the introduction of Dr. Wallis, please? May I request the person who's introducing Dr. Wallis to kindly take over and start his session, please?
Yeah, Dr. Preeti ma'am, I think Gareth Wallis sir is not joined yet.
No, he just joined.
In which name can you please tell? I can search it. Hello. Good afternoon and good morning to one and all. It is my pleasure to introduce the first speaker for today, Dr. Gareth Wallis. Dr. Wallis received his PhD in 2006 in the area of exercise metabolism and nutrition from the University of Birmingham, UK. He did his postdoctoral training at the University of California, Berkeley from 2006 to 2008 in the field of integrative biology. Dr. Wallis then worked in new product research at GlaxoSmithKline in a scientific program aimed at developing new nutritional products and health claims. He started at the University of Birmingham in 2012, where he now conducts academic research in exercise science with a major focus on nutrition and metabolism. He is currently working as an associate professor, reader in exercise metabolism and nutrition in the School of Sport, Exercise and Rehabilitation Sciences at the University of Birmingham, UK. His goal is to better understand how nutrition can be modified or manipulated to enhance metabolic or adaptive responses to exercise with a particular focus on macronutrients and their roles in performance, training, adaptation, and health. To study these areas, he utilizes a range of experimental approaches that enable detailed profiling of metabolic responses to exercise and nutrition intervention in humans. His research and approaches adopted aim to generate the translational knowledge needed for practical application within sport, exercise, and health nutrition settings. Now, with these few words, I welcome Dr. Gareth Wallis to deliver his webinar talk today. The topic is carbohydrate intake and recovery in sports. Dr. Wallis, please.
Thank you very much for the introduction. Let me just share my screen. Okay, so thank you very much for the introduction. Sorry, I had some login problems, so a bit delayed getting started. But first, let me thank you very much for the invitation to present to you all today. It looks like a great program, so hopefully you will take a lot from it. As the chair sort of kindly gave my background, I don't need to go over that, other than perhaps to say that I'm from the University of Birmingham in the UK, and we have a very long-standing educational relationship with India, and I'm pleased to be continuing that today. So my talk's going to be focused around the role of carbohydrates in recovery from sport, particularly a metabolic focus, and perhaps in line with the seminar sort of focus, it's going to be quite research focused. So things that you wouldn't typically see in the textbooks, and even some things that perhaps won't even be seen in some of the athlete guidelines at the moment, because some of it's quite contemporary. I'll try and relate back to the athlete guidelines where it's relevant, but much of it will be fairly research focused, and perhaps in the questions afterwards we can think about the kind of translational relevance for some of the sports that you might be involved in. So before I start, let me just provide you with some of the disclosures. Research requires funding, and these are some of the organizations that have funded me over the last few years. Okay, so two objectives of today, which I'd like to get through perhaps in the next 30 minutes or so. The first one is to describe how different dietary carbohydrates are metabolized during the post-exercise period. And then the second one is to discuss the potential relevance from a functional performance perspective of consuming different types of carbohydrates for recovery of subsequent performance during exercise. And just to put this in context, the talk's going to be focused on the kind of short-term recovery. So trying to optimize recovery over several hours after exercise for a subsequent bout. And that's because I think that's where you can have quite a big impact with the type of nutritional approach. When you have longer between bouts of exercise, for example, a day or 2 days, there's much more time for your habitual diet to kind of catch up and help with the recovery. That's not to say that recovery isn't an important, nutrition isn't important in recovery when there is a more prolonged recovery period. It's more that I think you can make, it has a greater importance when the recovery period is just a few hours. Okay, so we'll start with the first question, which is really around the metabolic side of things. So hopefully this slide won't be too much of a surprise for many of you watching, but these are just the different types of dietary carbohydrates that we would typically find in our diets. And so for the majority of population and athletes, hopefully most of their daily carbohydrates are coming from starch sources, so the storage form of carbohydrate in plants. So this would be things like potatoes, rice, breads, etc. But ultimately, starch is the chains or branch chains of glucose molecules depicted by the black circle here. And glucose, of course, is a monosaccharide, which is depicted down here, and starch is broken down and ultimately into glucose. Within the diet, there are also disaccharides. These may occur naturally within foods and drinks, such as lactose in milk-based products, sucrose in some fruits, or potentially added into products as well as added sugar. So these disaccharides, of course, are two carbohydrate types, so two monosaccharides, and these vary. Lactose is galactose and glucose, sucrose is glucose and fructose, and maltose, which isn't that common in the diet, in some beers, is two glucose molecules. And ultimately, again, they are digested to liberate one of the three monosaccharides. And it's these three monosaccharides that are ultimately absorbed into the body and have the effects within the body. And so my approach has very much been to be interested in, what happens to these three monosaccharides when they go into the body, and how can we understand more about these to take advantage of their metabolism for the advancement of recovery. So when they are absorbed, both glucose and galactose are absorbed across the intestinal membrane, first by this sodium-dependent glucose transporter, and then secondly via GLUT2, glucose transporter 2, and this takes the glucose into the hepatic vein, which then takes the glucose to the liver. Fructose follows a different absorption pattern, which you can see at the bottom of this slide here. So it uses glucose transporter 5 to get across the luminal membrane of the intestine, and then follows a common path as the other two monosaccharides, GLUT2. And I'll refer back to this these differential absorption pathways a little bit later. A brief recap on kind of glucoregulation, glucose homeostasis, just because it's relevant for where the talk will go. So when we are just kind of sitting, doing nothing, our blood glucose is maintained typically around 5 millimoles per liter. And if you haven't eaten anything, that's largely a result of the liver, which is a major storage site of carbohydrate in the form of glycogen, breaking down glycogen to glucose, and glucose being released into the bloodstream to top up any glucose that is disappearing from the bloodstream to help support brain metabolism and other bodily functions at rest. When you eat something, let's say you have some glucose, comes into the intestine, some of that will go to the liver, but some of it will also escape the liver and cause a rise in blood glucose concentrations or blood sugar. And of course, the body then tries to work to reduce the blood glucose levels. And it does this in a number of ways, which are primarily orchestrated by the release of insulin from the pancreas. The increase in insulin causes, it stops the continued breakdown of glycogen to glucose. So that's not a continued source of entry into the bloodstream. But it also causes the synthesis of glycogen in liver, and also the uptake of glucose into muscle and the synthesis into glycogen muscle, or indeed oxidation. Should point out here that the other two monosaccharides, fructose and galactose, when they're absorbed, they don't really create a large insulin effect. And in fact, they're not really metabolized peripherally. So they're mainly metabolized in the liver and stored as a glycogen or converted to other substrates. And again, that will become relevant. So the reason I'm talking about this is because what we all will be aware of is when we perform intense aerobic type exercise, we use heavily the muscle glycogen stores and also the liver glycogen stores, and they become reduced and in some cases depleted, and that in many cases is linked to fatigue during exercise. And so one of the goals in recovery from exercise, of course, is to try and replenish glycogen in muscle and liver. And there's been a lot of focus on the muscle over the years. And more recently, people have become interested in how we can optimize the storage of liver glycogen as well, with the view that if you can increase liver and muscle glycogen, then you will have better fuel availability for a subsequent exercise bout. So I'll take you back to a study performed in 1987, and it's really just to illustrate some general points about the metabolism in muscle. Study from Blom and colleagues, and what they did was exercise individuals to reduce muscle glycogen stores, and then following the exercise bout, they fed them different types of sugars, monosaccharides in this case. So on one occasion, individuals were given glucose at regular intervals in a 6-hour recovery period. So this was about 56 grams of glucose an hour, so every 2 hours, for a kind of, let's say, an 80 kilogram man like myself. So they gave glucose on one occasion and fructose on another occasion. And I've depicted glucose here because we know that glucose can be directly taken up into muscle and is a direct precursor for muscle glycogen. Fructose has these dotted lines because it's more likely that fructose is metabolized in the liver to something like glucose or lactate, and then that is subsequently taken up into muscle and used for glycogen synthesis. And they were interested in how does different types of monosaccharides affect muscle glycogen resynthesis? And this is what they found. So the 6-hour synthesis rate of glycogen when the individuals consumed glucose was just around 6 millimoles per kilogram of wet muscle per hour. Now, of course, the units are not particularly important to remember. It's more the relative differences between the sugars in this instance. So if we look at the fructose, what they found was approximately half the synthesis rate. So from this study, they were able to say that consuming glucose in recovery from exercise is more advantageous for muscle glycogen synthesis as compared to fructose. And that may be because the fructose is preferentially metabolized in the liver, so maybe it is not such a good source for muscle glycogen. One thing that intrigued myself a few years ago was that we really don't know very much about how galactose can be used to affect muscle glycogen synthesis. And there really wasn't any studies on that. So we embarked on a project to look at this a few years ago, and I'll share some of those data now. So this is just a picture of one of our labs here and the setup. So this is a study looking at how galactose affects muscle glycogen in recovery from exercise. We usually have somebody exercising on a bike intensely, and then when they're finished, they come off the bike. We'll try and sample a piece of muscle from their exercised muscles to be able to then analyze glycogen content. And then we would start feeding them different types of carbohydrates and take further biopsies over the course of a few hours of recovery to look at how that glycogen is changed. I'm just going to, somebody has asked me a question around explain the effect of fructose on blood glucose levels. So when you consume fructose, the effect on blood glucose levels acutely is much less robust than if you consume glucose. And that's primarily because fructose goes to the liver and some of it will be converted to glucose, but not all of it. So only a small amount of glucose is then released. Okay, let me carry on. So in this study, we had 9 individuals do a high intensity intermittent cycle to exhaustion to deplete their muscle glycogen levels. And then we fed them different types of drinks in recovery from exercise for a 4-hour period. On one occasion, they had glucose. On another occasion, they had galactose. And on another occasion, they had a combination of galactose and glucose. And the dose was always fed at 1.2 grams per kilogram body mass of carbohydrate per hour, which is in line with the kind of expert recommendations for rapid recovery from exercise after exhaustive exercise. And we took biopsies post-exercise and after the 4 hours to look at how much glycogen was synthesized. We had some other measures later on, but I'm not going to talk about those today. So what did we see? So if we look at our glucose trial, and this is just depicted in the same way as the Blom study, but with the new data, which is unpublished, inserted here. And this is expressed as the net increase in glycogen over the course of a 4-hour period. And we can see that the rate was 155, so the net synthesis, sorry, 155 millimoles per kilogram of dry muscle increase over a 4-hour period. And if we look at the galactose, what we can see is it was significantly lower. So rather similar to the fructose, the galactose was not as effective as the glucose as at restoring muscle glycogen. And that again maybe makes sense because of the predominant metabolism of galactose in the liver rather than it being potentially direct precursor for muscle. So we certainly know that the type of monosaccharide can affect muscle glycogen synthesis. Glucose is more effective than fructose or galactose. But what about the dose? And one of the nice things about the study by Blom from '87 is that they also had a trial where they essentially doubled the dose of glucose ingestion. So for a kind of 80 kilogram individual like myself, this would be just over 100 grams of glucose immediately after exercise, 2 hours and 4 hours after exercise. So that's quite a lot of carbohydrate. And what they showed, which was very interesting, is that it had no effect on increasing muscle glycogen synthesis. And this is quite consistent with the majority of studies now that have been nicely summarized in this work from Betts and Williams, and essentially supports the guidelines that athletes, the practitioners are given from expert academics to suggest that consuming 1 to 1.2 grams per kilogram body mass of carbohydrate per hour over a 4-hour period seems to be the maximal amount necessary for stimulating muscle glycogen synthesis. And I emphasize the muscle here because that's where most of the studies have been conducted. Now, one of the things that I was interested in a few years ago was, well, why is there a limit to muscle glycogen synthesis? Is it possible that once you're consuming too much glucose, you simply can't absorb any more, and therefore no more glucose can be made available for muscle glycogen synthesis? And with that in mind, and drawing on some research that we had conducted looking at different types of sugars being consumed during exercise, we hypothesized that if you combined glucose and fructose, this could actually increase the amount of total carbohydrate that's absorbed into the body by using 2 transporters instead of 1. And that may lead to an increase in carbohydrate availability for muscle glycogen synthesis. So we looked at this in a study which was published over 10 years ago now, where we had 2 conditions. Both conditions, individuals exercised to deplete muscle glycogen, and then they consumed either fairly large quantities of glucose only or a combination of fructose and glucose, 2 parts glucose, 1 part fructose. And we looked at muscle glycogen synthesis, which I've depicted down here. And we found that over 4 hours, the synthesis rate from glucose alone was around 44. And it really wasn't any different when we combined the glucose and fructose. And these rates are fairly high. They're consistent with what you get when you consume fairly large quantities of moderate to high glycemic index carbohydrates. So much to my disappointment, we weren't able to show that combining these 2 monosaccharides could increase muscle glycogen. Looking back, it's probably a bit of an oversight because we perhaps neglected the important role of the liver in metabolism of fructose at this point. And just to say that these data have been repeated by other groups as well. So thinking about the liver is probably an important aspect when we're trying to optimize which types of carbohydrates are consumed during recovery. So some work from a group in Switzerland led by Decombar and colleagues, which was published 2011, looked at what happens to the liver when you consume either glucose or fructose glucose during the recovery period. I've given 2 green ticks to the muscle glycogen here because we already know from the study that I did that the glycogen levels are similar with these 2 combinations. But what happens to the liver? Well, they were able to use non-invasive magnetic resonance imaging to measure glycogen in the liver, because you can imagine taking a biopsy from the liver is not particularly pleasant, but using an imaging approach is a good way to do this, although they are not that common around the world. When you do this from glucose, you see a synthesis rate over a 6-hour recovery period of just less than 4 grams per hour. In contrast, the synthesis rate when you combine fructose with glucose is more than double. So as we kind of thought might be happening, when you consume fructose and glucose in relatively high doses, there appears to be sufficient glucose to facilitate muscle glycogen synthesis. But equally, the fructose component affords a greater level of liver glycogen synthesis. And that again has been repeated by other groups. So what about galactose? Well, interestingly, in that same study by Decombar, they found the same effects with the galactose, that galactose plus glucose stimulated higher liver glycogen synthesis. One of the things they hadn't done was look at the muscle. And you might remember back to the study I showed earlier, the design, we actually had a study arm where we looked at glucose versus galactose plus glucose as well. So that was the question mark we had a couple of years ago, which we now have some results for. So if I kind of summarize this, we've got the glucose, where we know that it's not as effective as in the liver as galactose plus glucose, and we have the rate of synthesis from the study I talked about earlier, 155. So what happens with galactose and glucose when we look at muscle glycogen? Well, we actually see it's lower. So it's not similar to the way fructose and glucose works, in the sense that that seems to be similar to glucose. It's actually significantly lower. So it's less effective. So that kind of helps us to complete the puzzle, if you like, on how all these different monosaccharides work on their own and also interactively. So what we can probably say in terms of summary is that oral glucose is superior to fructose or galactose when consumed alone for short-term post-exercise muscle glycogen synthesis. Oral fructose or galactose, when co-ingested with glucose, is superior to glucose for post-exercise liver glycogen synthesis. And post-exercise muscle glycogen synthesis is similar with glucose and fructose, glucose and fructose glucose co-ingestion, but inferior with galactose glucose co-ingestion. So the take home there really is that if you want to optimize or enhance at least whole body glycogen storage, so that's liver and muscle, combining glucose and fructose is probably going to be superior compared to glucose only. And I've put source in brackets here, so I very much mean glucose fructose sources. It doesn't necessarily need to be pure glucose and fructose. So that might have implications for the types of foods that people consume that have higher relative proportions of fructose within them, for example. So that's the metabolism, and that's all well and good, and you know, academics get very interested in that. But one of the questions, of course, which is relevant is, what are the functional implications for these different types of carbohydrates? So how do they actually affect subsequent exercise capacity or performance? And I'll finish off by spending a few minutes talking about that. So in about 2016, I had a master's student who was very interested in this, and asked what I would say is a simple question. Does fructose glucose co-ingestion during short-term recovery from exhaustive exercise improve subsequent exercise capacity? Because we know that metabolically it appears to be favorable in terms of glycogen storage. So does this translate into a capacity benefit? He set up a study design whereby individuals ran on a treadmill or a fructose combined with glucose drink. You'll see here it says GLU-MAL. The MAL relates to maltodextrin, which of course is just branch chains of glucose. So it's essentially handled just like glucose. It's just an easier way to deliver large amounts of carbohydrates because it has a low sweetness. So we have a glucose only condition and a fructose glucose condition. They then were asked to repeat the treadmill test, so run again to exhaustion at 70% of their VO2 max. And we're interested fundamentally in how long do they go for in this second trial, and do they go longer with fructose glucose versus glucose only? And we took a whole host of other measurements as well. Yeah, somebody is asking me some questions. I think what I will do is leave the questions until the question and answer session at the end in the interest of time. So what did we find? Well, does subsequent exercise capacity enhance with fructose glucose? The simple answer is yes. So the time to exhaustion in that second bout of exercise, as shown here, was around 20 minutes or just over 30% longer with the fructose maltodextrin. So that's really nice proof of concept, if you like, that you can do some interesting manipulations with metabolism in recovery, and it does seem to translate into a performance benefit. We also took some metabolic measurements during that second exercise bout, and we were able to essentially show that the likely mechanism in this context for the performance benefit was because the greater storage of carbohydrate in recovery translated into a greater ability to sustain using carbohydrates as a fuel during that next exercise bout. And that kind of makes sense because we know that intense exercises needs to be able to use carbohydrate as a fuel. So the ability to sustain that is an important aspect of maintaining endurance. And we could also show that the carbohydrate that was utilized in that second exercise bout was the carbohydrate that we fed in recovery. And it's also always quite reassuring when other people find the same result as you. And a study came out last year from another group where they did something quite similar. They looked at fructose glucose versus glucose in recovery. They had a short experiment where they looked at a 4-hour recovery period, but they also did an experiment where people exercised in the evening and then were fed the carbohydrates, went to bed, and then did the subsequent bout in the morning. And what they're able to show, I'm just highlighting the key point in the abstract here, is that cycling capacity was greater with glucose and fructose versus glucose only in both the short experiment and the overnight experiment. And this is quite nice because, of course, they show the same effect that we had. This is a cycling model. We used it in running, so it's nice to see it in different types of exercise. And they also expanded it to a more prolonged overnight recovery period. Now, of course, when you publish results where you test someone's endurance capacity, i.e. their ability just to keep going at a fixed intensity, some people argue that that's not ecologically valid. It's not a test of performance. And that a real test of performance would be something like a time trial where you have to complete a fixed amount of work. And there's a whole debate in the literature about ecological validity. But one of the things we're interested in is saying, well, does it also affect subsequent time trial performance as opposed to just time to exhaustion? And this is a paper that was recently published this year. Very similar model that we've tended to use in Birmingham. In this instance, it was cycling exercise, and then the recovery was the glucose maltodextrin or the fructose maltodextrin. And in the next bout, participants were asked to do an hour fairly steady exercise and then do a time trial, so complete a set amount of work as fast as you can, and that typically took around 40 minutes. Rather disappointingly, we didn't see an effect here of the glucose, the fructose and glucose, or fructose and maltodextrin. So you can see here the time trial performance was almost identical between the two conditions, 38 and 37.4. So it just goes to show that you don't always get the results that you're expecting, and this also opens up, very interesting questions about, well, why might something work in one condition and not another condition? And not seeing what you thought you were going to see is almost as important as always seeing what you thought, because it helps you to understand when the application of certain approaches might work and when they might not work. One of the things that we think might be going on here is that in contrast to the study that we did with running and endurance capacity, in this study, we found that whilst there appeared to be greater storage and oxidation and use of the carbohydrate we gave in the recovery period, it seemed to be used up more quickly in that second exercise bout, to the extent that when they started the time trial, it's possible that the total amount of carbohydrates left in the body at that point was quite similar, and that might explain the similar results. But we don't know that for sure. That's just a hypothesis. So from that, we can say that the oral fructose and glucose in recovery increases the subsequent use of carbohydrate as a fuel of the ingested carbohydrate during the next bout. And that seems to work for enhancing endurance capacity, at least fixed intensity exercise where carbohydrate is an important source of fuel. So the potential that these approaches are, let's say, ergogenic versus glucose only is there. But because we didn't see the performance benefit in the more latter trial, we have to say that the exact specifications and applications required to take advantage of these kind of mixed sugar blends requires further clarification, so that we know when things may work and when things won't work, and that will be relevant for how athletes might apply some of these practices. So just coming back, just to sort of finish off, hopefully I've caught up a bit of time for us all here. We had two objectives. The first was to describe how different dietary carbohydrates are metabolized during the post-exercise period. And I think the data I've shown you shows that combinations of fructose and glucose appear to benefit short-term post-exercise liver and muscle glycogen storage. And remember, I've always used kind of pure sources of fructose and glucose. So it really takes a bit of thought to think about what types of foods might encourage these combinations of sugars within them, so that athletes aren't just chugging down sugar and water solutions all the time, but getting this from real foods. The second aspect was around discussing the potential functional implications of consuming these different things. So do the metabolic benefits translate? And I think what the data shows is that combinations of fructose and glucose appear to benefit subsequent exercise capacity, but not exercise performance in the conditions studied to date. Performance wasn't reduced, and I would always argue that you're probably better off enhancing the metabolic benefits than not. So consuming these types of blends is certainly not going to be detrimental to performance, but may actually be beneficial. So, and with that, I'll conclude. I'm just going to look at the chat. Yeah, okay, there's more questions. I think we'll take the questions at the end of there's a question and answer session in an hour or so after the other speakers. So with that, I'll just like to say thank you once again for the invitation for giving this presentation. Thank you for all listening intently, and I look forward in an hour or so to answering any questions that people may have.
Thank you so much, Dr. Wallis. Thank you for honoring us by accepting the invitation and extending your support despite being away from your place of work and traveling. You spared your precious time to be with us. Thank you so much once again.
No problem, no problem.
Yeah, and that was really a very comprehensive view on various carbohydrates, explaining in detail when to use a single monosaccharide and when to use a combination of carbohydrates to maximize benefits during exercise and for recovery. And I can see a volley of questions. And I regret that we may not have time for all the questions, but we will take up one or two key questions. And the others are encouraged to email us with their queries, and we will pass them on to Dr. Wallis for him to answer. We will try and take up the maximum number of questions given the time. And thank you once again, Dr. Wallis. Do stay with us. I also regret to inform you that our academic head, Dr. Bharti, tried to log in, and now she's been called for a very important meeting with the Ministry of Health, and she has sent her introductory note to us. And it is an honor to be able to share her note with all the participants. She says that it's a pleasure for me to launch this webinar series on sports nutrition of the MYAS-NIN Department of Sports Science during the symbolic National Nutrition Month of India. The Department of Sports Science is a scheme of the Government of India, Ministry of Youth Affairs and Sports, that started in the year 2018 at the ICMR-National Institute of Nutrition and is currently under the administration of the NIN. She says that the objectives of the department are mainly to develop human resources in the field of sports sciences, starting with sports nutrition through its MSc program and also through extension and training programs in the area and related areas. This series of webinars on sports nutrition is planned to bring to nutritional professionals, athletes, and the general population key emerging research evidences and best practices for promoting sports excellence. As you know, each webinar is designed to be covered in two halves. During the first half of the webinar today, research evidence and experience will be shared, or more appropriately now has been shared, with a focus predominantly on carbohydrates and their metabolic influence on recovery from exercise for training and sports. Our international speaker from UK, Dr. Wallis, shared his insights on the utilization, depletion, and replenishment of carbohydrates with respect to intense training and its effects on recovery and sports performance. The second half of the webinar that focuses on tools, techniques, and best practices or skills will describe the research tool for measuring energy expenditure, bringing out differences in its usage among samples from general population versus athletes. Both these areas are key to athletic performance and regular monitoring of athletes. While being contemporary to sports excellence, the topics are also sought after in research currently. Through this first webinar, we hope our participants will receive and update their information on these crucial research aspects and one essential tool for sports nutrition research and its monitoring. I'm sure the webinar will continue dissemination of similar research information and skill development in the current areas of sports nutrition continuously. I wish the department the very best. I now hand over the session to our sports nutrition team for the introduction. She said to the first speaker, but I'm going to say to our second speaker, Dr. Mansi Chopra from New Delhi. So it's over to the sports nutrition team for introduction of Dr. Mansi Chopra. Thank you.
Good afternoon, everyone. It's my pleasure to introduce our next speaker, Dr. Mansi Chopra, who is going to talk about energy expenditure tools and measurements. Dr. Mansi Chopra has done a PhD from All India Institute of Medical Science and Lady Irwin College. She was working as the Deputy Lead and Senior Consultant at the National Center of Excellence and Advanced Research on Diets, Department of Food and Nutrition, Lady Irwin College, which is supported by UNICEF. To her credit, she also has led a portfolio on maternal and adolescent nutrition, including development of the antenatal nutrition, high-risk pregnancy guidelines, and communication toolkit for the Ministry of Health and Family Welfare, Government of India. Her research interests include development of low-cost lifestyle interventions for management of non-communicable diseases, body composition, energy metabolism, and maternal malnutrition. She has published several research papers and reports in international peer-reviewed journals and has presented her research at various scientific national and international conferences. It is our pleasure to have you here, ma'am. We would love to hear from you. Thank you.
Thank you so much for the introduction. I will first share my screen. So at the outset, I would like to thank the organizers and the departments for inviting me to deliver the lecture on energy expenditure tools of measurement. In brief, the outline of the presentation will involve what energy requirements really are and certain tools in which I would be mainly talking about the heart rate monitoring method, which has been used for comparison of energy expenditure computation between young adults, wherein 15 were sedentary and 15 were athletics who were playing basketball at Lady Irwin College. So before we start and look at the tools of measurement, we should first understand what energy requirements really are. So our body really needs energy for maintaining temperature, certain kind of metabolic activities, and for supporting physical work and growth. And as defined by the FAO, it is the amount of food energy which is needed to balance expenditure and in order to maintain body size, composition, and a level of physical activity which is consistent with long-term good health. And there's several factors also which we need to keep in mind when we look at energy needs and requirements, because there's so many factors which actually influence energy needs that include age, it includes gender, it includes body size, the amount of physical activity, and then climate and altered physiological status, and a lot of disease conditions. So when we look at all these things, we need to understand that if we keep these factors in mind, is only where we would want to understand what the requirements are, and then we can use a tool of measurement. So when we look at estimation, we have two things. We have an intake and we also have an expenditure, which then we can use to compute energy balance. But our human energy requirements are estimated from measures of expenditure. Plus, we also add additional needs, which may be for growth in terms of when children are growing, or also in terms of physiological status like pregnancy and lactation, where there may be more amount of growth of tissues and other things that are involved. So all these accompanied together constitute the requirements of energy. And why we use energy expenditure is because it is not as varied as intake, which may be very different for different individuals every day. And there are three components of energy requirements also, which we need to understand. So the first is basal metabolism, which contributes to our energy expenditure and requirements. The second is a metabolic response to food or thermic effect of food. And then we also have our physical activity, which is the most varied domain in terms of contribution towards the entire requirement. So just going over each of these three, we need to understand that we have a basal metabolism, and this is mainly nothing but our essential bodily functions that happen every day and which are essential for life, for which we need energy, like cell function and replacement, synthesis of tissues, secretion and metabolism of enzymes, hormones, maintenance of body temperature, then cardiac, respiratory, muscle functions, brain functions. All of those are these functions for which we require energy. And the rate that we talk about is the amount of energy which is used for basal metabolism, which is the lowest rate of energy use in a period of time. And what we usually do is that it is measured under standard conditions, wherein a person is awake in supine position for 10 to 12 hours of fasting, 8 hours of physical rest, and mentally relaxed in ambient environment temperature. So this is actually just the basic minimum amount of energy which we would require, which is the basal metabolic rate. And it represents around 45 to 70% of the daily total energy expenditure. And why is it so varied? Is because it is determined by a lot of factors that include age, gender, size, composition. There may be genetic predisposition to having a metabolic rate, exercise or physical activity, any kind of infection or illness can also increase the metabolic rate or decrease it. There is growth, which is there, endocrine system, the menstrual cycle in females. If we go on crash dieting, starvation, use of stimulants, all of these factors are some things which contribute towards determining the basal metabolic rate of individuals. The second component that we talked about was the metabolic response to food. So what is this metabolic response? Is that we all consume food, and this food has to be digested in our body. So as we've already looked at and heard the presentation of Dr. Wallis, there is a metabolism in place, and we have carbohydrates, proteins, and fats, which are metabolized to glucose, and then eventually to water and carbon dioxide. So for the energy which is needed for ingestion, digestion of food, and for absorption, transport, interconversion, oxidation, and deposition of nutrients is the thermic effect of food. And it usually increases the total energy expenditure by about 10% over the BMR for 24 hours, and is usually computed on a mixed diet. And recently, it is also known as the specific dynamic effect or specific dynamic activity of food. And based on your physical activity, whether it is the duration and intensity, it may also have certain effects on the amount of thermic effect which we have in our body. And the third component which we talk about is the physical activity. And this is the activity or the movement of any bodily skeletal muscles to perform activity which will lead to an expenditure. And it is the most variable component because every individual will have its own set of activity duration, intensity, frequency. And it may include obligatory activities which may be dictated by economic, cultural, or societal norms, like occupational activities, the work that we do. And it also involves the discretionary activities which are are important for maintaining good health, well-being, and quality of life. And as it is the most varied component, it roughly impacts around 20 to 35% of the total daily energy expenditure. And when we look at this, this is something which is most related to sports nutrition, because all the activities that are conducted would come under this particular domain of energy expenditure. So this has been explained in terms of the metabolism of carbohydrates before me. However, we need to understand that when we are looking at any kind of sports or exercise, there is a contraction of muscles which would require some kind of energy. And the basic unit which is there in our body is the adenosine triphosphate, which is converted to ADP plus a phosphate group to release some of this energy for our functions. However, we need to understand that in our muscle cells, we have a limited supply of ATP, which can only provide energy for about 3 to 5 seconds. So what we really need to understand is the resynthesis of this ATP from ADP, which is generally required so that we can sustain our life as we are doing every day. So we have three systems in place which the body can use, in which we have an aerobic system and an anaerobic system. So I will not go into the details of these systems because this will be dealt in your classes. However, when we look at the aerobic pathway, it is dependent upon oxygen consumption. And when we look at the anaerobic pathway, it is independent of oxygen consumption, in which we also have two systems, which is one is the lactic acid pathway, and the other is the ATP creatine phosphate system, which may be used. But we need to really understand is that these pathways depend upon, some would be required for intense activity and some will be required for when a person is like running marathons, cycling, and other things. So one system is used over the other will actually really depend upon the duration of the activity, the intensity of the activity, and the type of activity. In addition, the level of fitness that a person will have will also contribute towards which system will come into place to provide this particular energy. So this is a brief of all the energy systems that we have and where and all we can actually use them. So when we look at our anaerobic systems of ATP, PC, and lactic acid pathways, the ATP, PC can be used, which is in an exercise which is of very high intensity for a duration of 10 to 15 seconds. Like when we sprint, or we have a 100-meter or a 200-meter race, when we have weightlifting, is where we need this particular kind of this system will be used. But we need to understand that we have small muscular stores of ATP and PC, which are exhausted quite quickly, and they can be rapid decline of immediate energy, and hence we need to have our second system in place, which is the lactic acid system. And the fuel or energy source for this is glycogen or glucose, and the byproducts can be pyruvic acid, which can then again go back and use glycogen or glucose, or we have the lactic acid if when produced is a byproduct which may cause rapid fatigue in our body. So after doing an activity, we have a general sense of fatigue which sets in, is only because of lactic acid production in our body. And this is also used for high to moderate exercise intensity, and up to 3 minutes is where we can use this particular kind of system, like at 400, 800-meter races, racket sports, badminton, basketball, all of these in some parts will also be looking at this lactic acid pathway for energy provision. And the last pathway that we talk about is our aerobic system, which may use fat, glucose, or our proteins. And the end products of this are water or carbon dioxide. And these are mainly used for long duration activities, 3 minute onwards, like marathons, cycling, races, etc. And this system is dependent upon availability of oxygen. So we have all these cycles in place. I've not gone over through cycles, but these are the systems which are usually required. And based on this, we need to understand that we have various tools that we now use for measurement of expenditure. So we know that we will be doing some kind of activity which will lead to expenditure, but then there are so many methods that are available. As an overview, I will only give certain methods, but in detail, I will talk about the heart rate method as well as the results that were obtained in our study. So the first method that we talk about is the doubly labeled water method, which is actually the gold standard for measurement of energy expenditure, and it uses stable isotopes of oxygen and hydrogen, which is deuterium, to compute energy expenditure. And it is used in a wide range of population, and it also can be used for infants, pregnant, lactating women, as well as elderly. And what usually happens is that we have these equations in place that are used for computation of energy expenditure. And we need to understand that when we talk about all these tools of measurement, there are certain equations that are available for specific age groups, for different ethnic populations, based on gender, body composition, and also being validated. So it depends upon what our target group is, what are our requirements and objectives of our study. Only then and also the resources available through which we should ideally be selecting our methods of measurement of expenditure. Then when we look at our second method, we have calorimetry methods also that are available. And when we look at direct calorimetry, the principle where it works is through measurement of heat loss, which is there when the subject is actually in the calorimeter, and all the activities that are performed there keep going on. And the measure of heat loss which is there is used for quantification of metabolic rate. And this is actually the most accurate method. And there may be the different types of direct calorimeters also that are available, which can be used for computation of energy expenditure. And then we have our third method, which are the indirect calorimetry. This method actually works on the principle of measurement of inspired and expired gas volume, as well as the concentration of oxygen and carbon dioxide. And we have equations which are also there. I've only stated one of them, but then similar to, as we spoke about calorimetry and DLW technique, there are many equations that are available which can be used to compute energy expenditure from them. And various methods are also available for gas collection. We have a Douglas bag, canopy, and a face mask. But the patient or the subject has to be there for a certain period amount of time for computation of energy expenditure using this particular method. Then the latest methods that we talk about these days are accelerometry. And we have a lot of accelerometers that are now available, which are validated with the DLW technique also, and can be used for expenditure. They're portable and can be easily used. And it is actually based on the principle of measurement of body's acceleration, which may be used in any kind of physical activity. And it is the change of velocity over time, and it is expressed in terms of multiples of gravitational force. And now there are many models that are also available, wherein we have one plane, two plane, or three plane models that are there for acceleration. Usually we use the triaxial model for measurement of expenditure. What the output which is generated using these accelerometers are counts per unit time. And then once we have an equation in place, we can use those to convert our counts into energy expenditure. And this expenditure can be either in the form of metabolic equivalents or in the form of kilocalorie per minute. So this on the right hand side where you can see this table is nothing but to show that there's so many accelerometers that are available. But what we need to understand is that there may be sensors and other things that are there, but for every activity, we need to measure that energy expenditure cost of that activity. So we have validations of in research, we have validation studies of accelerometry through with heart rate method, or with the subjective methods, or with the DLW technique for different activities, say for running, for sitting, cycling, for dancing, etc. So we need to understand which method and which tool we are using and how valid this is, and then we can come up with our particular equations which can actually be used to calculate expenditure. Our next methods that we use are pedometers. They are not they're easy, yes, to be used, but not mainly used for energy expenditure, because some of the models also display expenditure. However, they are not validated with gold standards, so we should vary of using them. And it is mainly used in the measurement of walking, which is the best activity and the majorly popular activity among populations. The output which is generated is step counts, and what one can do is with this step step counts, we can also calculate the distance traveled, which is through multiplication of these steps with the stride length. And the stride length also is dependent upon the way a person walks, the speed, height, age, and gender. So pedometers are also widely available, are being used, but mainly for assessment of the amount of physical activity or the number of steps, but not mainly for measurement of energy expenditure. And we also have subjective methods in place that are used, and they're the most widely used methods of expenditure because they are cost effective, they can be easily used, they give you information about physical activity patterns, and in terms of the frequency, intensity, duration of physical activity that a person performs. And they include physical activity questionnaires, records, diaries, etc. And the most commonly used methods are the International Physical Activity Questionnaire. We have Rapid Physical Activity Questionnaires, GPAC, which is by the WHO. Then we have physical activity recalls, which actually can be used for 1, 3, or 7 days, and records as well. And what we usually do is that once we have this particular activity in terms of the amount of activity which is done, we have a physical activity ratios or the energy cost of that particular activity, or metabolic equivalent to tasks of those activities, which can be used for computation of total energy expenditure. Another thing which becomes important here is the computation of the physical activity level. Here we have a categorization of a person into an activity level, which is maybe sedentary, moderate, or heavy. And this is computed by the total energy expenditure, which comes from the activity record, which is divided by the basal metabolic rate for 24 hours. We also have Indian specific equations, which are given by the ICMR, but we can use FAO equations and others also to compute BMR and eventually PAL for activity categorization. So these are certain advantages and limitations of these different energy expenditure methods, where when we talk about the DLW, it is highly accurate, is actually a gold standard, and it allows a freedom of activity. However, it is very high in cost, very expensive analysis and equipment is needed, and expertise is also required for the personnel, and the method does not provide any specific details on the kind of physical activity that is performed. Then when we look at direct calorimetry, it is also a most accurate method for quantifying metabolic rate. However, it has high cost, and subject confinement is required for 24 hours or more and may not be convenient for subjects. Then when we talk about the indirect calorimetry, it is accurate and non-invasive. It provides information on the metabolic fuels which are being combusted, and also can be used in field settings. However, it again has a high cost, and trained personnel will also be needed for the methods correct use. And when we talk about the accelerometer technique, it is objective, is being widely used these days because of the models that have come in. It can be used in both lab and field settings. It is non-invasive and is less burdensome to subjects, and is relatively inexpensive as well. However, we need to understand that when we compute accounts to energy expenditure, we may have predictive equations which may not be that accurate and valid, and hence we need to understand that once we have these equations which are valid is when we can actually use this particular data set or these tools. Then pedometers are, yes, inexpensive and can be used in field settings, but it is mainly limited to walking, but the data that we get may not be able to translate into energy expenditure. And self-report methods, as we said, may have low accuracy and reliability, and it is linked on participants' memory. So usually it overestimates the energy expenditure that we compute from these methods. So looking at the heart rate method, which we will now go on to, it is based on the principle of estimation of expenditure, which has a strong positive relationship which exists between the heart rate and the oxygen consumption. We really need to understand that there is a linear relationship between the heart rate and the oxygen consumption, and is specific to each individual. And with development of these small instruments which measure now minute-to-minute heart rate for long periods of time, it has considerably improved this technique applicability to the measurement of expenditure. And what we usually mainly and most commonly use are a wristwatch, where as shown is this picture. So we have a lot of models that are available, which are also valid, and also a chest band, which actually measures your heart rate minute to minute. And the data is captured in the watch. And there are many protocols also that are available, which can be divided into a resting phase, an exercise phase, and a post-exercise phase, and we can also compute energy cost of activities using these particular methods. And a lot of validation studies have also been conducted on different population groups with having different activities or varying intensities using this HR technique. So studies have also shown that we need to understand it is individual, because there's so many factors that affect the heart rate. There may be environmental factors like noise, light, temperature. There may be physiological factors like cardiac morphology, plasma volume, autonomic activity. Any kind of disease may have a impact on the heart rate. Then even mood, emotions, stress, and other related conditions can have an impact on heart rate. Then we have non-modifiable factors like age, gender, ethnicity, as well as lifestyle, like fitness, the sleep duration, medication, intake of tobacco, alcohol, and the intensity, modality, body postures. All of these affect heart rate. So when we look at combining heart rate data as a group, then we see that there is a lot of variation as compared to when we look at individual energy expenditure. So these are certain things that we need to keep in mind when we are using this heart rate monitoring method, that we need to come up with individual equations between heart rate and volume of oxygen to compute energy expenditure. There was another term that was coined in the late 1980s, which is the flex heart rate, and that became the standard tool for measuring daily energy expenditure in free living humans. What this flex heart rate is, that it is the highest heart rate at a basic minimum position, where if you're sleeping or you're resting, so that is the highest heart rate, plus when we use the lowest heart rate at a particular physical activity. So before starting an activity, that heart rate, and and the sleeping highest heart rate is something which is the flex heart rate, which is the inflection point, is the term which is used to compute our energy expenditure. So in our study, which is experience of using this method, the paper was published in 2015. We used a cross-sectional design, and our young active women were basketball players, 15, and we also had age-matched sedentary women from Lady Urban College, New Delhi. We had a set inclusion criteria in place because we understand that heart rate method is affected by a lot of factors. So we wanted all women to be unmarried, in the age range of 18 to 23 years, no history of disease, because that can have an impact on heart rate, not suffering from any kind of respiratory illnesses, not consuming any hormones or drugs, women in the pre-follicular or pre-luteal phase of the menstrual cycle, and also involved in active sport for at least 1 hour per day, 5 times a week. And for sedentary women, similar criteria was set, except that they were not mandated to have at least 1 hour per day of activity. So what we did was that we used the Polar Sports Tester heart rate monitor and a Polar Whirling transmitter individually on all participants who wore this watch and this particular belt for 1 working day in their non-sleeping hours. And with this, what we did was that to also use another method, we used the activity record method, and using the factorial approach, we also computed energy expenditure for the same day using both these techniques. And after this, what we had to actually do was compute the HRVO2 relationship curves. So this was individually computed for all people, and these curves were computed using the cycle ergometer and oxygen analyzers at DIPAS, New Delhi. And daily records of ambient temperature, humidity were also recorded, because they can also have an effect on the heart rate and oxygen consumption. So we use the Monarch ergometer to actually provide the slope and intercept of the line relating to energy expenditure and heart rate. And what we did was that after every 2 minutes, before resting, we increased the workload and gave 2 minutes for the subject to actually get used to the new level of work. And then we computed the oxygen and heart rate. And the flex heart rate was the mean of the highest pulse rate at resting and the lowest on exercise, plus an additional factor of 10 was added to it. And then we calculated the regression equations individually for all participants. So we used consecutive readings of oxygen and heart rate for subjects when they were idle on the bicycle ergometer, and then as the wattage increased the loads, we can computed these particular values. And the RMR was calculated by multiplying the oxygen which is consumed with the calorific value of 5 kilocalories to convert oxygen into energy expenditure. And for heart rate, which was above FH flex, corresponding expenditure was calculated using the time spent at BMR plus the time spent at heart rate which was less than FH flex, and the time which was spent at heart rate more than FH flex activities. So and you can actually see a graph. This heart rate is actually going up to 190. So for this individual subject. So after we gathered this data in our wristwatch, it was through an infrared device or transported to any kind of laptop which can be used. And then we had the minute-to-minute data, as well as we had these graphs which were automatically generated for every individual participant. And when we looked at the results, we could actually see that, yes, they were age matched and in the age range of 20 years, but we also saw that there was no significant difference between the anthropometric and body composition variables, also between the active and the sedentary group. So these are also some factors which affect heart rate. So we also saw no differences between them. And when we look at the data in terms of anthropometry with body composition variables, we can see that the correlation coefficients range from 0.8 to 0.9, probably going up to 1 as well. So we had high correlations between weight and body composition measures as well. Here, what we did was that because it was an energy balance study as well, that was one of the objectives. So we computed the total daily energy intake and expenditure using these two methods. And what we really saw was that in terms of the energy intake, it was 1800 and 1500 kilocalories between active and sedentary group subjects. However, when we looked at the heart rate data, that was closer in terms of the energy which was being expended by these two groups as compared to the factorial method. So the total daily expenditure was around 36% higher with the heart rate method, and with the factorial method, it was 27% higher among the active group. But we need to understand that the factorial method actually gave 16% higher values than the heart rate method for group A, and 12% higher values for group S. So we could really understand that it is better to use an objective method of assessment, because it was clearly very near to the intake data as compared to our factorial method, which was overestimating, as is based on a participant's memory. Then these results were actually individual HR to HR VO2 relationship curves, which we had actually generated for group active and the sedentary group. Here we can actually see that we have the oxygen consumption on our Y and our heart rate on our X axis, where we computed individual regression lines. And we can actually see that the correlation coefficients were very high, around 1.99 up to 1 between these individual regression lines also, which were computed using 5 data points for, and then these equations were used to compute energy expenditures. And in addition, what we did was that this was something which was important in terms of when we look at physical activity level data and the amount of expenditure which was being done in both the sedentary and the active group. We also categorized the time and the energy expenditure which was spent during sleep, as well as in activities which were more than flex heart rate and activities which were less than flex heart rate. So we saw that there was no difference between the time and the calories which were spent in sleep. However, there was a huge difference between, and a significant difference between the time which was spent in more than flex and less than flex activities between both these two groups. and it was pretty significant. However, we need to understand that on an average from our study, which was the main finding, was that it was 70 minutes of activity which was spent in sports, and the physical activity level was 1.79 in this particular group, and which was in the moderate category, as compared to the sedentary women who had a physical activity level of 1.43. So the corresponding expenditure which the active women every hour, every day per hour were spending was around 164 kilocalories, or 2.4 plus 0.3 kilocalorie per minute, or 3 kilocalorie per kg body weight every day. So this was the amount of expenditure or an hour of activity which would actually convert our sedentary women into our active women, from a sedentary to a moderate physical activity level. So this was something which was very important. And we also saw that the heart rate method gave precisely closer estimates to the intake as compared to our factorial method, which overestimated our activities. So there are many uses also of this energy expenditure data. So it is extremely important nowadays, because in the global context of NCDs, obesity, and all these diabetes, hypertension, which are increasing. So we really need this particular data. It helps and is used in surveillance, epidemiological, clinical, and intervention research studies. The data that we get from energy expenditures can also be used to derive predictive equations. We can develop newer instruments that are valid and portable for use, and are can be used for validity of existing instruments as well. If we understand the expenditure data and the activity pattern, then we can also use this particular data to develop individual diet plans for management strategies of disease conditions, and for sports and athletes as well. We can track daily expenditure and activity patterns. In addition, now this data is also being used to determine longitudinal changes in expenditures among populations, and it can also in the end motivate people to have healthy physical activity routines and lifestyle if we use accelerometers or wrist watches, which can give you heart rate and energy expenditure data. So when we look at recent literature, there is so much of so many studies that are happening on heart rate, on different kinds of tools and measurements. On PubMed, you can, if you only write energy expenditure method tools, you get around 14,000 hits or even more. So to just emphasize, there's so many studies that are happening on newer methods for validation purposes, when we can also use a particular method to understand whether it is accurate to estimate energy cost during low intensity or high intensity exercises. There are so many research activities in terms of validation of one instrument with the other. There are review studies that are there. In addition, this is important. We have so many compendiums of physical activities. These are METs, or physical activity ratios, or energy costs, which are actually used for subjective methods, particularly to compute energy expenditure data for a day or a week. And so these are some highlights of publications that have happened over the past 5 years. So depending upon your own objective, the resources, and the sports that one needs to look at, we can use the heart rate method technique because it is valid and can easily be used for research purposes. Thank you.
Thank you so much, Dr. Mansi, for your insights into various methods that we can use to measure energy expenditure. You also covered in detail all the equipment that is available and can be used, and the benefits among of all these methods and equipment amongst various population groups, and while designing specific studies. And it's very encouraging that there are so many participants who have joined us. It's been our maximum limit so far. I mean, we've never had such an overwhelming response before. And I regret that many of you are waiting in the waiting room. I suggest that you all please go along with the link on the YouTube and join us at on the YouTube page. And we'll be able to take up just a few questions in the question answer session due to paucity of time. but stay with us and today view the entire session on the YouTube, because there's a surprise waiting at the end of it. And with that, I request the person who's going to be introducing the third speaker to take over and kindly introduce our third speaker. Over to you.
Good afternoon, ladies and gentlemen. It is a great pleasure for me to introduce our last speaker, Dr. Keren Cherian, who is going to present to us about estimation of energy requirement for athletes using factorial approach, individual versus group. Currently, Dr. Keren is working as a scientist and teaching faculty member of MSc Sports Nutrition Program under Myers and Department of Sports Science. She has done her bachelor's and master's in food and nutrition from Women's Christian College and pursued her PhD in ICMR-NATIONal with UGC JRF branch. Her areas research experience are energy expenditure, energy availability, and body composition for adolescent athletes. She is a young researcher passionate to develop sports research and educate the athletic fraternity on food, nutrition, health, and performance. Her areas of interest are relative energy deficiency in sports, body composition, energy expenditure, recovery nutrition, and sports nutrition. Dr. Cherian attended many national published research articles in the area of sports nutrition. She is also an accredited level 2 anthropometrist by ISAC. It is our pleasure to have you in this webinar. Now I will hand over to Dr. Keren. Thank you. Please, ma'am.
Thank you so much, Sudeshna, for that wonderful welcome. I would just share my screen. Give me a second. Yeah. I'm sure it would have been a very exhaustive session for all of you. And then you're down with the last speaker. So this is not going to be a very theoretical session, hopefully. It's a more of a practice-oriented session so that, you know, we get to know hands-on what we could do in real-time athletic situations. I appreciate and congratulate the organizers for initiating the sports nutrition webinar series. So I'm sure that there are a lot of topics in sports nutrition that is of interest to everybody. So before we move on to the practical aspects of other nutrients, let's just get the energy straight so that that becomes the basis for giving any kind of fuel guidelines for the athletes. So be with me, and if there's any questions, feel free to put it in the chat box. Yeah. So my topic is, as already stated, estimation of energy requirement of athletes using factorial approach, individual versus group. So Dr. Mansi has made my job pretty simple by giving the brief introduction of how energy requirements are set, etc. But still, I would like to give you an overview, especially pertaining to what are the kind of variation in energy expenditure that we observe among athletes, and why is it important to estimate energy expenditure or energy needs based on the individual, and when can we, you know, sometimes we have to give a menu plan for the academy and we need to estimate how much energy to provide for a group as well. So this is a more of a practice or skill based session. We base our energy requirements predominantly on the energy expenditure, as already stated by Dr. Mansi, and mainly we have three components, that is the basic components: resting metabolic rate, thermic effect of food, and physical activity. This is common for everybody, and when you look at the theoretical illustration, just give me a second. So if we look at a normal population and athlete, what is the difference in the energy expenditure pattern? Now that is very important. If you look at the components of energy expenditure, that is basal metabolism or resting energy expenditure, we see that in in a healthy adult, you will see around in the range of 60 to 80% of their energy expenditure would be directed to the resting metabolism or resting metabolic rate. But if you look at an elite or a professional level athlete, you would notice that it would be much lower, like especially in their peak competitive season, their energy expenditure towards physical activity has been observed, even in my studies, close to 50% of the total energy expenditure. So therefore, when we plan a diet, for being a nutritionist, when we plan a diet or give recommendations for a healthy adult, we might, of course, it should be aged and gender matched. I have an issue with, yeah, I hope you're able to see my slides. Yeah. When we look at a normal healthy adult, we see that the variation in RMR, or the RMR contributes maximum to the total energy expenditure, which is around, it can vary from 60 to 80%. And the physical activity level of a normal healthy adult would range from say 0 to 30% based on the level of involvement in any form of physical activity. But that's not the same case with the athlete. And therefore, it is very important to actually assess or determine the physical activity training load or intensity. So when you look at energy for athletes, it's very important to notice that the variation in physical activity is very, very important. And that is something that we need to tap, right? Having said that, energy balance is what we are looking at. And there are times when the athlete, because the weekly schedule keeps varying from high to low to rest states, and they have a varying level of intensity of training across the whole week, right? So it is a lasting state of weight changes, particularly in certain sports like weight dependent sports, strength or combat. The lasting changes of weight are higher. There are times or zones or time points in training where these athletes might go into a low energy intake state or a higher energy expenditure state, and this in the long run can lead to a lower muscle and fat mass. Now, before it leads to a reduction in the muscle or fat or body mass changes, what the body actually tries to attempt is that, being provided the lower energy intake, how can I manage with what is being provided to me? So there are some adaptations that the body undergoes. Now, how do they do this? They do this predominantly by reducing some of the hormones secretions, especially the reproductive hormones, that is the gonadotropin releasing hormone, FSH and LH, and also the thyroid hormones, leading to a lower production of estrogen and testosterone. This has been reported across various studies, and this actually causes your energy expenditure to be reduced to match what is being provided. However, this might not be good for your long-term health. It can cause a deterioration in your long-term health. That is why when you look at energy for athletes, it's there's also this concept that has come to be, because there's a varying audience. I would like to introduce all this before I move on to my topic. Energy availability. So that is, how much of energy do I have after my exercise energy expenditure has been subtracted for my health, for maintaining my health or bodily functions. This was mainly, studies were mainly carried out on the associations with a health outcome, predominantly on female athletes, and on menstrual health outcomes and on bone health outcomes. So there were some cutoffs initially developed, and it has been established that is energy available state less than 30 kcal is found to affect or cause some changes in your menstrual function, and also for your bone health. And particularly for an athlete who's training at a very high rate of intensity, these kind of situations occur where they go into a low energy available state. So it is important to look at energy. So most of us give recommendations or nutrition guidelines based on this, where we say that, okay, it should be higher than the 30 kcal so that they maintain their normal functioning or health. However, when you look at the training protocol of an athlete, we see that only basing, so energy availability is a concept that is good for us to understand the health outcome or in relation or to protect the athlete from energy deficient state. But there are also times in his training schedule and where there is a lot of changes, where he would be in the energy sufficient state, or the energy expenditure would still hold good for us to understand how much to provide. Okay, and that is important because there is changing individual goals, there is changing training levels, and the requirements change throughout a season or a training cycle. Now, to explain this better, I would like to show an example of this macro cycle, which is the yearly calendar, which all the athletes generally would have. And this colored marks show different seasons in which they would be playing at a high intensity, low intensity. Also, the mesocycle provides you what kind of training would they be undergoing at a certain state, and also what energy systems, as already mentioned by Dr. Mansi, what will be tapped for during those training hours. Now, if you see, there are a lot of colors here. I mean, what I want to emphasize here is that there is a lot of variation across various training intensities and protocols, and it will, if you give the same energy throughout the yearly calendar, it might not suit the need of the individual athlete. Now, that is the reason where periodized nutrition means each and every strategic use of nutrition in terms of fuel as well, in terms of energy as well, to support what the exercise protocol that the athlete is presently following is like very key. So moving on, how do you see, what are the kind of variation that you see in particularly exercise energy expenditure from reported studies? Let's just look at the first example, that is done on an individual variation. This was reported in 2019, where they compared the exercise energy expenditure of 6 male professional cyclists. So across the 6 male cyclists, they found on race days, there was a variation of one cyclist had around 4,400 calories expended, and versus 5,920. So there is a huge gap of around 1,500 calorie difference. On rest days also, there was a variation of 650 to 1,060. So at an individual level, doing the same type of activity also, the exercise energy expenditure varied drastically. And this holds good for us to understand why it is important to arrive at an individualized energy need or expenditure. Playing season variation. So this was also reported in 2013 by Reed, where they looked at energy availability and tried to understand what are the differences in energy availability across the season, where they found that mid-season there was around 35 kcal that per kg fat-free mass that was expended, versus post-season, where there was a higher energy available state. Why? Because the training intensity was lower. So yet again, I would like to give another example of a study by Moss et al. The data was presented as follows. The type of exercise or training which is provided in a weekly schedule. For example, in a week, there might be days where they train heavy. There might be days where they train light. Now, what is the difference in, let's first look at the exercise energy expenditure. There was a difference of like say 15 kcal per day at rest to around 881 kcal on a match day or on a heavy training day. So this is a huge variation within a week. And if you look at the EA, that also varies. That is, of course, rest 42 kcal and on a match day 29 kcal per kg fat-free mass. If you look at the, now just turn your attention to the middle table, that is energy intake, which shows that it is constant throughout all the training. There was no significant difference in the energy intake across the various days of training. This brings light to many of our recommendations as well. So if we fix on a particular energy or calorie based on not following an individualized approach, we might give the same calorie on days where there is match day or rest day. So this is something that we need to look at as nutritionists when we plan or calculate or plan for diet or menu or any other stakeholders, even researchers for that matter, right? So moving on to determining human energy expenditure, I wouldn't go in depth into this because already Dr. Mansi has covered this. However, giving a basic example of glucose oxidation here, I'd like to give a perspective of how do we estimate energy. For example, this is a basic glucose oxidation that you can see, and we can determine energy from the work that is generated the work, whenever we do a work, for example, I'm talking here right now, there's some kind of heat that is produced, and that is the internal work generation or production. That is measured by the direct calorimetry. If you look at the external work that happens outside the body, most of our measurements rely heavily on the movements or external activity. That becomes the work that we can calculate or identify externally. And also, if you can also indirectly measure calorimetry, that is utilized to metabolize this glucose into energy, right? And the amount of carbon dioxide that is produced in the process. Now, one assumption of the indirect calorimetry is that the cellular respiration or the internal cellular respiration that happens is same as what happens externally, or the external respiration. It is the same. So that is one assumption that we have to understand. And so if I'm sitting and I'm having a measurement done for an indirect calorimetry, that means I would be using different metabolic cards to assess it. And when I do that, what I actually get is, for sitting, how much is the energy that I expend? And similarly, for various activities, we extrapolate using the indirect calorimetry. So again, what it actually says is that the indirect calorimetry is equal to the direct calorimetry plus the external work that is done. So this is a perspective on given by Professor Paul, which is quite, I feel, quite easy for us to understand. Now, moving on to this pictorial representation of various components of energy expenditure when it comes to looking at measurement from the point of view of measurement. If you look at doubly labeled water, which is of course the reference standard, we can get all these components in one go, and it is a cumulative assessment. So it is an average of 7 days or 7 to 14 days based on the intensity of training of the athlete. And from which, if we have to arrive at the resting energy expenditure, we generally have to use even thermic effect of food, indirect calorimetry methods. For the activity or physical activity as it was known earlier, now it is also divided as a non-exercise activity thermogenesis and the exercise energy expenditure, where we can use the following techniques that you can see. There are varied amounts of techniques, and Dr. Mansi has given a brief about the heart rate monitoring method and the accelerometry approach, which are of course very useful and handy on field assessment of energy. However, in case of when we look at practice, it might not, especially in the Indian setting, not every athlete might have access to a heart rate monitor or an accelerometry. Therefore, the technique of observation is also useful in the absence of any other methods that you could, is available at your service, or if you don't have access to any of the other methods, right? So today I would be talking or giving a brief about the method of observation. How can we observe, like athletes monitoring? How can we do a monitoring, and probably take you through one approach, because there are a lot of approaches, and one approach that has been carried out by me for my PhD as doctoral work. And also we have some research evidence also to back it. So the individualized total energy expenditure by the factorial approach. The step one is, of course, here is to identify the time spent in activities. For convenience, I would divide the activities into training and non-training, because how you record it matters, and therefore it is important to understand that these two have different types of activities, right? So there are two approaches again where we can take here. That is, one is self-reported, reporting by the athletes, where the error might be slightly high. However, we are looking at a guideline here in the absence of not be feasible in the field setting. Or direct activity monitoring. So this is directly, this might be more time consuming. That is, somebody has to observe the activity done by the athlete, which is not popularly used. Even in research, in sports, many of the publications so far make use of the self-reported activity recording, provided there is a strict pro forma and how you collect the activity is clearly explained to the athlete, right? Moving ahead, the step 2 is we need to arrive at or have some basis for determining the energy cost of activities. There are various approaches here as well. However, today I would be dealing predominantly with the existing database on metabolic equivalence. So what is metabolic equivalence in simple terms? So it actually basically is defined as the ratio of work to that of rest. So what does that mean? The one met or the basic, if you take one met, it means that it's the met for rest, and how many times rest is sitting, how many times rest is standing. So it is actually multiples from rest. So if you have to determine or if you have to use any met value or any compendium giving metabolic equivalence values, one thing that you need to do is understand what is the RMR or the resting energy expenditure, because if the RMR varies, because most often if you're taking the compendium of Ainsworth, as I would be here, the met, that value that they have given is 0.9 met, and calculated all other mets based on the 0.9 met as the met for rest. So if the met for rest for athletes or the energy cost for rest for athletes will vary, then that would cause a variation in all the other intensity of activities that you would be extrapolating. So this is something that you need to keep in mind when you are using. So therefore, you need to correct for the resting metabolic rate. The most ideal approach would be to measure resting metabolic rate using an indirect calorimetry. But again, since we are talking about a field-friendly approach, we could use prediction equations. And the next question in mind would be, which is the accurate one that we could use presently? Okay, so I will probably clarify all these things that you might have doubts in. We'll go in detail. So the basic calculation that we would need then is the energy cost of a single activity. We need the time spent in that activity. For example, if I'm sitting, then the time spent in sitting. The RMR per minute of the individual. If it is myself, I need to have a means to calculate that is even can be valid as well, not just calculate an RMR, and multiply it with the met that is provided in the compendium. So there are a lot of compendiums. Now in this example, in this session, I would be going at for the compendium of physical activities given by Ainsworth, predominantly because through our studies also we compared the energy cost of direct measurements using indirect calorimetry as against that met values developed in Ainsworth, and we found that the compendium of physical activities were suitable for most of the majority of the activities. So that is another reason. And then how do we arrive at the total energy expenditure? We add up all the energy cost of these independent activities to arrive at 24 hours or 1440 minutes. Now moving forward, you can see this is a very exhaustive table, but I would just like to draw your attention to the RMR prediction equations, that these are a lot of listed equations that were validated as part of my research and against the indirect calorimetry method. And we found out that the equation of Cunningham, which is highlighted in red, and all the other equations highlighted in red, was found to be suitable for Indian athletes with very less than 5% deviation. And therefore, in this example, I would be using the Cunningham equation to arrive at RMR. We also have the equation of Wong et al. That was suitable for the Indian setting. And also, Soares et al. Had developed an equation for Indians, and that was also found to be suitable in this particular study, which was published in 2018. Moving on, so how do we record activity? So there are various ways in recording an activity. Today, I would be using the time allocation pattern, which was given by Satyanarayan et al. And Venkatramana et al. And this basically is a very simple in activity recording form or performer, where the time, posture, activity description is marked. This can be done on an Excel or any other programming can be done for easy access. But for your understanding, I'm giving a minute by minute calculation of 15 minutes of a non-training activity. So you can take the approach, because non-training activities generally don't vary much. it is the training activities that vary a lot, even in case of an athlete. So because of that, you could take the approach of getting based on the accuracy needed. For example, if it is for research, you might want to get a minute by minute variation. And if it is for a regular practice, you can go up to an hour or hourly calculation of the non-training activities, which I would not recommend for the training activities. And how do we then code it? So we list out the activities, then we have a coding, that is the W is a short form for walking, ST is standing, and S will be sitting. So the subscript here 0 is denoting to the intensity of the activity. So 0 can be low intensity, 1 can be moderate, and 2 is higher intensity. Now, how do you differentiate this? Like if low intensity are those activities which do not have much of a movement. For example, if you're climbing up and down stairs, that's again called walking, but it is a higher intensity. So you would want to give W2 in such situations. And this is important for you to classify, because then it gives, we have a tabulation column that we can use to arrive at how much of standing idle or at low intensity standing is. And then probably we'll use the MET values that is provided in the Ainsworth to calculate how much of standing activities. For your convenience, I'm using a 15 minutes calculation here. And moving on, I would also tell about the training activity recording. That is, here I have taken an example of a adult soccer player. Around 30 minutes is recorded. So if you look at from 7 a.m. to 7:30 a.m. is what I have recorded. Minute by minute recording is there. And the first activity is warm-up jog, which I denote by W jog. You can use jogging or any other term that is convenient for you, but this is what we have used. And there is also a component in athletes that we need to write down whenever we are writing an activity, or whenever an athlete is monitoring an activity. It is important to know the number of the distance traveled if it is jogging, and the number of repetitions or sets. The same goes with weights as well. If they're going with weight training, it's important to understand that, because that gives us an idea of the intensity. Or I'll also come to how this, for example, this jogging would give us an idea of how much speed he travels. So he travels 1,200 meters and for 10 minutes. Then what is the distance he would travel in an hour? So this is how we get to what kind of speed he's traveling at, and that is very, very important when we have to identify MET values using the compendium. So another thing that is important when you record for training activities is that the standing activity in between a training bout. For example, if an athlete is like after jogging, he just stands for a while or he walks for a while, that cannot be same as that of the standing normal or during non-training hours. So therefore, it is very important for us to identify what is that is called the interspersed rest, and it is nothing but during training he's standing. So that will have a higher MET compared to, or a higher energy cost compared to the normal standing that he will do. Next is the conditioning drills. So it's always good to describe the activity as and when he's doing, what is the type of activity it is, so that it will help us to code later. And then he involves in a 10-minute soccer match. This is what where he's ball passing or running with the ball, etc. So this has been described. Moving on, then we tabulate it. What are the types of activities? We name the activity as it is and list out the time in minutes and get the 30 minutes. As I told you earlier, so let's just calculate for jogging. So we'll get around 7.2 kilometer per hour, or approximately 5 miles per hour. Then we move on to the compendium, which we can use to arrive and then check for the exact MET value. These METs can also be coded in an Excel, and it would become very easy for you once you list out all the activities. You would not have to do this exercise regularly. It becomes easier for you, right? So here we see around 8 MET. Okay, this is the value that we need to use for jogging. So similarly, you will have to look for other METs as well. So if I'm taking the example of a soccer player and an average body mass of an Indian soccer player around 65 kg, of which 56 kg might be muscle. This is just an example. And calculating RMR using the Cunningham equation, which is around 1.2 kcal per minute. Moving on to the earlier calculation that we saw, is the time spent in the activity multiplied by the RMR per minute into the met value. We tabulate it. It can be, this is for your convenience and for your understanding. You can tabulate it using a programming language or in Excel, and it's up to your convenience, right? So for this, if you can see, I've listed out the activities. It is around 30 minutes. And also we are correcting for the RMR. So in the compendium of Ainsworth, the RMR is 0.9 met. However, if I'm calculating based on the prediction equation, this particular player's RMR is around 1.2 kcal per minute. So it needs to be corrected for in the met code and arrived at the total. So you multiply all these three together to get at the total activity energy cost. And then when you total the entire excess activity schedule, for example, in this case, it is 30 minutes. So you get a total of 221 kilocalories. So this is just an understanding for you, because you can use this in your field as well. So one thing is that for the interspersed standing, you might not find an activity code, or you might have to relate it. But this was also measured in my, it will be soon published. So it's available also in research gate. So if you want to use any indispersed activity energy cost, that has also been reported or tabulated. Moving on, so now this is how you would use a protocol to arrive at the energy requirements at the individual level. Now, even at a group level, because we would be needing or requiring a base support for planning menu at an academy or a sports academy. Still, NIN has done a lot of studies in the past, led by Dr. Y. Venkatramana, who has retired now, and he has developed a lot of energy expenditure studies and developed these grouping or classifications of events based on the intensity or energy expenditure rather, and provided a guideline as to how much of grouping, like across various groups, what is the ideal body weight and what is the kilocalorie allowances in general. I'm sure this needs to be updated. It was first, last published in 2010. However, it still holds good if you want to look at a group energy expenditure or a recommendation for a group of athletes rather than individual athletes. So another approach also would be, if you want to look at the same approach, take on an ideal body mass of, based on the table here, I have used the group 3, which is around 65 kg. And I have same way using the Cunningham equation, we have arrived at the total RMR or RMR per day. You can use the ideal body mass, or if you're in an academy and you have anthropometric measurements of athletes, you could take the mean value of that and use that to arrive at the RMR based on the ideal body mass or based on the fat-free mass. Based on weekly training schedule, we have to identify the physical activity factors, and then we have to put in those values as well. And right now we have taken, like I have taken around 2.2 activity factor and around 4,250 calorie I have got. If you look at the previous table, it is around similar, like if you look at the 5,200, around 4,550 to 5,200, it is around the similar calories. So if you want, the present prudent approach would be to use a group recommendation and arrive at the energy expenditure. And that's about it. The concluding remarks would be, it is always good to arrive at individualized energy expenditure, and energy availability assessment separately need to be focused for the Indian athletes, because most often we might use the energy availability but not following the individualized energy expenditure assessment, since most of the athletes get a schedule or a macro cycle, and then of course they might have variations within the week. It is easier for us to arrive at an energy expenditure for a single athlete in the beginning, and then follow it up with any minor changes with the coach that he or she might have throughout a week or a month. The accuracy of the factorial approach is dependent on the activity recording. So care must be taken to either educate the athlete or you have to observe it directly, or most often coaches also have quite an influence on how much activity what each does, and that also could be advantageous if we can get the training schedule from the coach and use the RMR prediction models. That is also important, because if the RMR prediction models is not suitable for our population in our country, it might also cause some amount of variation in the energy expenditure. However, presently we have validated and we have some methodology to follow. We can develop or build up on this in future. If you look at for menu planning in a sports academy or a group, calories can be fixed based on prevailing recommendations in the absence of others, which might be coming up in the future. So it's the most prudent approach to stick to for a group. It's most prudent to stick to prevailing recommendations, or you could use any activity factor or any other factor that we can that is commonly available and accepted, but the variation might not be much is for a group level, because anyway you are not looking at an individual variation there. So with this, I would like to thank the organizers for giving me this opportunity. I'm basically part of the Maya Department of Sports Science. And as already introduced, we are academicians as well as researchers, and we are in the initial stage of getting into research, and we are looking forward to providing more information related to sports nutrition in the coming years. Thank you.
Thank you so much, Dr. Keren. Keren is our in-house ICMR faculty, and she knows how we are striving in this baby department to bring to you what maximum we can in terms of research insights as well as extension. There are a couple of questions, and thank you so much, Dr. Wallis, for staying on with us, and Dr. Mansi. So due to paucity of time, I'll pose just two questions to Dr. Wallis that is not related to the quiz that we are going to post on the chat box. And one question each to Dr. Mansi and Dr. Keren. And I will ask you these questions together if you allow me, so that we can save some time. And I will post the link to the quiz based on the webinar in the chat box. So the participants who are logged on with us in the Zoom platform can use the link, and this link will also be sent out on the YouTube page. So coming back to the questions, the two questions to Dr. Wallis are, firstly, what is your opinion on consumption of natural drinks such as sugarcane juice and coconut, because they are very popular in Asia? And the second question is, how would the timing of carbohydrate ingestion affect the glycogen resynthesis? The question to Dr. Mansi, could I just ask all the questions, just two more, and then we can kind of take the answers, all the answers one after the other. I'm sorry for taking that liberty. And the question to Dr. Mansi Chopra is, can we estimate the effect of season or climate on the energy requirements in clinical practice? And any estimates in percentages to reduce or add to your energy expenditure? What is the current evidence on it or current view on it? That is the question to Dr. Mansi. Season or climate changes and energy requirements. And the question to Dr. Keren is, what formula did you use to calculate fat-free mass in the study that you are quoting? And with that, I call upon Dr. Wallis to answer his questions. I know this is a little innovative method of question answer session, but viewing the paucity of time and the eagerness of our participants to enter their feedback form, I request you to kindly bear with me. Dr. Wallis?
Thank you. Yeah, I think I answered those questions in the chat directly when they were posed, so people can.
Yeah, Dr. Wallis, there are a few people on the YouTube who probably cannot view the chat. Yeah.
So I'll start with the timing. Yeah, the evidence suggests that earlier feeding of carbohydrate, so within the first hour or so of exercise, is likely to result in a higher rate of muscle glycogen synthesis compared to delaying, for example, for a couple of hours, at least when the recovery period is short. So if we're talking about a 4 to 6 hour recovery period, if you have a good day of recovery, then the timing may be less important, but the amount of carbohydrate is important. So as long as you consume, probably somewhere in the region of a minimum of 5 grams per kilogram body mass carbohydrate, you're going to get a good restoration. The more you consume, the higher the glycogen synthesis over 24 hours. But I think if it's short-term recovery, then yeah, earlier ingestion is important. In terms of natural drinks, I think it's quite difficult to comment without knowing the composition exactly of these particular drinks, but there's no reason to suspect that the types of sugars in natural drinks wouldn't be advantageous for recovery. If it's sugar cane, which I presume then is sucrose, well, that's glucose and fructose, so that would be very good for glycogen synthesis. I'm not familiar with the exact profile of sugars in coconut water, so it's difficult to comment, but remember also that the fluid element will help with hydration. So I don't think there's any reason that they wouldn't be effective as recovery aids. Yeah.
Dr. Preeti ma'am, can you please unmute yourself?
I'm so sorry. We are reversely getting muted and unmuted for that. And yeah, right. Yeah, I'm unmuted now, but Dr. Wallis is muted. Can we have Dr. Mansi's answer, please? So the Zoom link is has been forwarded by me on the chat box, as well as by the NIN official chat box. So you could use that Zoom link to answer the quiz, please. And sorry for being unmuted in conversation. Dr. Mansi?
Ma'am, can I answer the question?
Please, yeah, please do.
So the question was to if we can estimate seasonal or climatic changes and its effect on energy requirements. So we have equations in place that can also be used, and factors which can be used to estimate climatic conditions. However, we need to understand that we have expenditures which would be the studies to show that there is more amount of energy expenditure in colder climates, and also is dependent upon the thermal regulation, which will also has to be added as a factor when we are looking at expenditure in climatic conditions. So there are factors and variables that are there. The simulation studies also that have been done based on this, and data specific to Indians is also available with the factors that can actually be used to counteract the effect of climatic changes. However, when we look at a population, we should keep in mind that we maintain our temperatures and humidity for all subjects so that we can counteract this particular effect as well. Thank you.
Okay, thank you so much, Dr. Mansi. Can we have Dr. Keren's answer?
Yeah, so for my doctoral research, we have used the anthropometric approach because that was more convenient in field. But for the example that I gave, it was just an example for us to understand based on a published paper. So it was just an example for us to just get an understanding of the practical session. That's it. Yeah. But in athletes in general, of course, the reference standard is DEXA, and we can also, most popular methods of measurement, because it has to be measured regularly. Anthropometry is accepted provided you have a skill training that you've undergone, and ISAC, of course, is offering skill training. Also, based on the practice, it becomes more accurate. So you need to have the practice of identifying the bony prominences, because if we make a mistake there, then we don't get the fat mass corrected. So.
Thank you so much, Dr. Keren. And now we will move exclusively to the feedback session. So the link has already been provided on your chat box. Kindly use that. And for those who are on YouTube, please use the link from the YouTube page. And so that we will view the answers to the quiz and send you the certificates. Hopefully within 1 hour, but given the network issues, if there are any network issues, then within the next 24 hours for sure. Yeah, we've started to get the quiz responses. We've received about 10. So it's working. So may I request Mr. Subroto Day to kindly give the vote of thanks?
Hello. Am I audible, ma'am?
Yes, you are.
Yeah. So, thank you so much, ma'am, for giving me this opportunity to propose the vote of thanks. And finally, it's the time to wind up together. So almost from starting, you already have listened to all the presentation. So now the time to club all these things. So on behalf of the organizing committee, ICMR Department of Sports Science and Extension and Training Division and entire ICMR-NIN faculty. So this is the time where I can say I would like to express my gratitude to our respected director, Madam Dr. R. Hemlata, ma'am, for his continuous support and giving all the arrangements and starting from the approval and these things. Really, I thank you, ma'am. My sincere gratitude to our academic head, Dr. Bharti Kulkarni, ma'am, for giving and this opportunity to all of us, and in taking this initiation to such kind of webinar series, particularly in sports nutrition. Although due to some other work, ma'am is busy, and suddenly she was engaging with that. That's why ma'am couldn't able to join with us. And she through his regards to all of you. Thank you so much, ma'am. I express my heartfelt gratitude to our administrative head and Department of Training and Extensions Division and Mycelium Department, Dr. M. Maheshwar sir, for his continuous support and suggestions and different aspects how we can improve this webinar. Thank you so much, sir. And of course, my sincere thanks to our respected eminent speakers. Dr. Gareth Wallis from University of Birmingham for his wonderful presentation on the subject carbohydrate and its recovery, particularly in sports. Thank you so much, sir, for accepting our invitation or giving this lecture in this platform, although he's very busy on his own schedule. Thank you so much, sir. Our second speaker, Dr. Mansi ma'am, for giving the orientation different energy expenditure tools. I hope our participant from the point of view of sports nutrition, they have learned a lot of things. Thank you so much, ma'am. And our last speaker, she is Dr. Keren. She is from our faculty for enlightening that area, particularly energy expenditure and of course different factorial approach, which is really important for this current situation, in particularly in our sports. Thank you, Dr. Keren ma'am, for enlightening our participant. Now the time to thank all the team, particularly organizing committee, from starting to Dr. Pritilisi ma'am for planning and guiding us, and Dr. B. Hari Krishna sir, Dr. Sainath sir, Dr. Jagdish sir, and our technical supporting staff, Ms. Sudeshna, Ms. Kavana, our research scholar, for their entire team from the planning to today's program. Although you know that this kind of webinar is not easy to plan within a day. So long back ago, in terms of timing, if you say from week back, we have planned, and today we have tried to give our best. So I really thank to all the members. Last but not the least, as this is virtual program, so definitely whole credits in terms of arranging this, it goes to our computer division, our teachers, those who are entire team of computer division, starting from, from technical point of view, from related to other areas like from how to do the registration and certification. So especially I should mention Dr. Munikumar sir and his team, particularly Narendra ji, for his support, and even till yesterday night they have done a wonderful job for these elements. So I really thank to all of you, your team. And also I should mention special thanks to our different stores, like from starting printing, our lab staffs, and each and everyone from Mycelium Department of Sports Science for their entire work, and today what we have presented to us here. So on behalf of entire team, I would like to thank all of you over here in Zoom meeting, and of course those participants who are in right now in YouTube. So every program is then success only based on the participation. So this is very important. So I would like to thank all of you for your kind patience and listening us and valuable feedback. So hope in coming time we'll also be organizing, and stay tuned with us. And finally, I would like to thank all of you. If somebody is missing, those who are directly and indirectly involved in this program, I would like to thank all of you. So now I can say it's like a memory, it's like a experience that we have learned today from our eminent speakers, in particularly sports nutrition. So all of you have enjoyed, and I believe you will take some good messages from our presentation. And I would like to say right now, goodbye for all of you. Thank you very much. Thanks a lot. Over to you, Dr. Pritilisi ma'am.
Thank you so much, Subroto. And I was caught inadvertently stating what I meant to state in the end. Both you young scientists, Mr. Subroto and Dr. Sainath, from whom we learn so much. They are so young, so energetic. Thank you for being on board and for bringing in all the energy and the technology and being hosts for today's webinar. Thank you both. And what I'd like to convey to our participants is that the session will be automatically logged off at 6 p.m. So we already have received a lot of certificate generating quiz responses, and we will wait for all your responses till 6 p.m. Thank you all for joining us today, and goodbye.